Hello, everybody. Thank you for attending the talk here. Today, we're going to talk about the life of an automated update. Um, we're going to cover a few different areas in this talk: changes in builders, branches and versions, merging code, as well as the automated update mechanisms that we actually use to ship uh, updates to our users. So, taking a step back here, to keep Chrome OS improving, we need to keep updating our software, which requires a number of tools along the way. So developers write new CLs that get reviewed in Gerrit. These get built and tested on our infrastructure, qualified for release within our release tooling, we call it GoldenEye, and deployed to our users using Omaha, the dl.google.com service. This presentation will dig into each of these areas in more detail to walk through the life cycle of a change. But this is kind of incomplete. There's really more to it. And although we're not going to talk about the other direction so much here, this really is a continuous cycle. Users provide feedback, including automated crash reports, which become bugs that the engineering teams work on, thus completing this loop and hopefully resulting in a product that continues to improve over time. So, first, a CL is created and built. To start with, the developer comes up with a change list. This is Google parlance for a patch. I'll probably say the word CL over and over again, uh, and that just means patch. It is a change that somebody makes. So with the CL on their local workstation and working locally for them, the CL is uploaded to our code review tool called Gerrit. It's actually public. Anybody can see this here and watch the code be reviewed. The change is reviewed by other developers, and feedback on the change is collected. The author of the change will then take the feedback and make adjustments to the CL, and then upload it again, forming a sort of code review loop here. Now, once the review comments are all addressed, and an authorized reviewer gives a +2 approval on the CL, it's ready to go on its way to land. The author marks the CL with a verified commit queue bit, and the CL makes its way into the commit queue to actually land. Now, you might ask, what is the commit queue and what is the CQ thing? Let's talk about that next. So, the commit queue is made up of a set of builders. These are called Paladin builders. So if you see the word Paladin somewhere on a CL that you're working on or in the code base, that's what it's referring to, uh, a commit queue builder. These take a CL, build it into an OS image that can then be used for testing, and it initiates tests against it. If the build and tests all pass, the CL is then merged. And if not, results are added back to the CL in Gerrit, and it is up to the author to review the results and fix the CL, or try for submission again if it looks like the results are due to some existing flakiness. There are a variety of other builder types as well, and we'll go a bit deeper into these in the coming slides. But to start, we have the pupper or pre-flight release builders, firmware, and factory builders. The pupper or pre-flight builders are used for bringing in large components, which are not built as part of Chrome OS itself. An example of this is the Chrome browser or the Android container for the Play Store on Chrome OS. These builders are similar to the commit queue builders in that they are only that they are more automated. Uh, no CL needs to be marked ready for these. They just scan for new versions of their component, try them out, and then land them into Chrome OS. The release builders are very simple. They are what we build what is actually distributed to users. So this is very similar to what you might build on your workstation at home. The firmware builders build, anybody guess? Firmware images, and the factory builders build factory test images, specialized images for use in factory lines to validate the new hardware as it comes out. Now, let's walk through the steps the CL goes through to land. First, it is marked ready, like we discussed previously. Then it is handed off to the commit queue. If you have a CL on Gerrit, you can see the commit bot making comments on the CL as it progresses. Usually this should come back positive, and the CL will be merged by the bot. If it fails, though, the bot will provide information as to the failure. It'll tell you some test didn't work or some compilation bad happened, and it's up to the author to act upon that. Eventually, when the CL does successfully build and pass tests, it is merged into the code base. And from there, the release builders will pick it up, and ultimately, the end users will be able to get that change. If the change is worthy of bringing into a release branch, it can also be merged there as well, where the same basic process is followed, enabling the CL to be available faster to users than just landing in TOT, or tip of tree, as we call it. The We'll discuss branches and merges in detail a bit later in the presentation as well. So that's just a normal Chrome OS CL. On the Chrome OS side, if the changes in the Chrome browser, the process is a little bit different, as this means one is working with the Chrome browser side infrastructure. It's actually very similar, though. The flow is basically the same. The browser has a commit queue as well, and the CL must be made to land there. After the CL has landed in the browser code base, there's a little bit more to do before it actually shows up in Chrome OS. Here we see our first use of Pupper. This mechanism scans for new versions of the Chrome browser and attempts to bring them into Chrome OS. This actually leverages the same mechanisms as the commit queue for a normal CL. In these cases, we're kind of effectively looking at two different CLs. First is a CL that is the change to the browser itself, which the author wrote, and second is the CL on Chrome OS itself to use a newer version of the Chrome browser. What the pupper mechanism is actually doing is generating that. uh, and then once both are landed, the CL is actually in effect at that point. So if all goes well within a day or so of landing a Chrome browser change, that will appear in as functional in Chrome OS. But there's a bit more latency there as it has to go through this flow. So now these are not visible to the public attendees. The Android stuff actually works in the same way. So if you've used the Play Store on Chrome OS, uh, this is how that gets in there. We basically have build infrastructure on the Android side that builds images. We didn't need to recreate that within Chrome OS, so we just use that. And very similar to the Chrome implementation, we have a mechanism that takes the Android binary, tries it out on Chrome OS, and if it's good, it lands, and ultimately it makes its way out to our users through the release builders. So if we look at the firmware, uh, this is looks a little bit more complicated, but it's really just a similar concept where we build in one place and then we bring it in another place. So looking at firmware, this consists of a few different components. Whenever I say firmware here, this is like the BIOS or the embedded controller software on a device. We use a special branch and builder for these. We build these independently of Chrome OS itself, primarily for stability purposes. Because this is very critical to get right. And it tends to not change very much because we want it to be very stable. This is the software that allows your device to turn on, so we don't want to get it wrong. The firmware builders basically work off of these firmware branches that are dedicated normally to a particular device or reference design. They're similar to release builders. They just don't bother to build most of the other packages of Chrome OS. They only build the firmware packages. So like I said, the BIOS and the embedded controller firmware itself. Uh, Now, getting that firmware into Chrome OS involves having the firmware branch build that image of firmware, having that image tested by firmware testers, and then uploading that binary to a binary storage location. And from there, the CL is made into Chrome OS itself, which references that binary. And this allows it to be used in release builds at that point. So this effectively takes a binary from a different source, puts it into Chrome OS, and then it is in effect at that point. So it's a very similar pattern we have with a lot of these things. With Chrome OS, it's quite broad and complicated, so we need to take steps like this to bring things in an efficient manner. So if you were wondering what builders actually do, they actually do a lot of things, and there's many steps involved here. This kind of shows the steps involved in a typical release builder. This is meant to be an eye chart. There's just a lot of them, so don't read it all too quickly. But really, there's just a few main things that these builders do. Um, they and these can be categorized in just a few main areas. So we broke it up into four here. So the first thing is preparing to build. So this is cleaning everything up on the builder, ensuring that everything is in place to actually build everything. So like making sure that the compiler is there and stuff like that. So next thing we do is we actually build. This is compiling everything, doing all the linking, bundling together actual OS images, and then after that, we need to do some additional operations on these images to make them usable for everybody, really. The things like signing the images and creating binary delta payloads, because we don't want to ship an entire huge image to every single user. We want to ship like the smallest thing we can, and so we generate those at this stage. And then we, of course, save them in an archive location so that we can access them later. And then the final type of thing we tend to do in the builders is kick off a bunch of tests so that we know how good the build is, and that we can find regressions as quickly as possible. So if you look at the logs from a builder, uh, some of the key steps you might see are described here. If you've built Chrome OS yourself locally, you've probably seen some of these or seen very similar things. So manifest version sync is analogous to repo sync. This updates your sources. Setup board prepares the necessary tools and such for building a particular board, which is our term for binary build target. So if I say board, I'm not necessarily meaning like a physical board. This is a build target. Sync Chrome downloads the version of the Chrome sources that will be used in a build. Uh, build packages and build images are just like we do locally. They compile everything and bundle together an OS image, and then the signing, page in, and archive stages sign images, generate binary delta payloads, and save everything to storage. So you might ask when we actually run these things. For TOT, we effectively build continuously. We target for 3 Chrome OS release builds a day, but based on how long they take, that basically means the builders are busy all the time. So we're kind of continuously building TOT. For release branches, the 2 most recently cut are build nightly. They're scheduled to run based on Chrome browser releases builds being cut. When a new release of Chrome browser is detected, a new version of the same milestone of Chrome OS is started. Chrome browser cuts a new Chrome version on TOT every day at around 8 p.m. Pacific. The 2 most recent release branches are cut at 5:30 and 5 p.m. So this basically results in we have a nightly availability of release builds for our release branches. So we can make builds of Chrome OS, but how do we stabilize these things? And as all these CLs land, because there's a lot going on here, and not just because we can land everything on TOT and maybe even we do test everything in advance doesn't mean that it's 100% good right off the bat. So next we can talk a little bit about branches and version numbers in Chrome OS, which is kind of how we achieve stability. Uh, Now, Chrome OS uses a 6-week release cycle today, meaning every 6 weeks we cut another release branch. And this begins the stabilization process. So the branching looks something like this. Note that after we cut a branch for release, TOT becomes the next milestone. So if you see R43 branching in the middle there, R43 on TOT actually starts 6 weeks prior. And as soon as R43 branches, TOT becomes R44 and so on. So it's a little bit misleading in the diagram because TOT is just one branch, but the milestone that it's uh, representing changes over time. So there's more to it than from a perspective of actually releasing, though, as we have multiple release channels that users can subscribe to. Uh, so from a release perspective, it ends up looking something like this. As we branch, every branch steadily moves forward towards stability over time. This is where the stability properties of our release channels actually come from. So if you're familiar with Canary Channel, that is the highest risk. It is constantly taking new CLs on a daily basis. These are basically coming directly from the TOT. Dev channel is fairly risky, but less than Canary. It has a bit more testing associated with it, and part of the time it's actually coming off of a release branch. So you make actually a big step in stability with dev. And you take another even bigger step with beta. The beta is actually fairly reliable because it has been on a release branch for at least a couple weeks. This means it's had time for testing and fixing of issues since we've made the branch and have started the process of stabilizing it. And of course, stable as well. Stable. It's been on the release branch for a long time, has a great deal of testing done to it, and any known blocking issues will have been cleared already by the time we get there. Now, if we follow along the channels, we can get a view that looks something like this. Here we trace through what a user on a particular channel actually receives from the various branches that exist. As we discussed, Canary's flat against TOT. Dev oscillates between TOT and a release branch. Beta's in the mid-region of a release branch at all times, and stable is on the outer end of the release branch at all times. Now, this also brings the concept of milestone promotion, where a particular milestone gets a new channel when the prior milestone gives up that channel. So this promotion effect actually flows down through the milestones, allowing each to move ahead by one channel of stability. We generally use the last release on the prior channel as a release candidate for the next channel. So, for example, the last beta of a milestone is probably the same build that will get used as the first stable of that milestone. So here we can actually see we have R42 being promoted to stable. This frees up the beta channel so that R43 can promote to beta, which frees up the dev channel so that R44, which is on TOT at this point, can promote into dev channel. And so now that we know all about these branches and channels, how do we keep track of what came from where? Uh, And to do that, we have a versioning system. And this actually maps directly to our branching system. With Chrome OS, we have two major types of version numbers. We have the browser version, which starts with a milestone number, then a branch version, which is really a daily build version. For example, we have built 2,785 browsers off of TOT for this particular example. Uh, and a branch build version, which is how many times we have built off of this particular branch. The browser actually has numerical branches. So the version here is R53, which was cut at the 2785th daily build of Chrome. And this is the 87th build from that release branch for the browser. The Chrome OS version actually works somewhat similarly. We call it the platform version if you look for it in your device. It lacks the milestone number though, and it adds an additional digit of depth. Uh, we have the major version, which is the number of times Chrome OS is built so far. This increments approximately 3 times a day. As we described earlier, we try to build that 3 times a day. The minor version number, which is the number of builds from the branch point, and a patch number, which is for builds from a branch of a branch. So in this case, we have a release branch build that was from the branch cut at the 8,530th Chrome OS build, and this is the 77th build from that branch, and it is directly from the release branch as the patch number is 0. So for Chrome OS versions, this maps to release branches, something like this. So this might be easier to see what I'm going for here. The first digit are major version increments on TOT, the second digit increments on branches from TOT, and the third digit or patch version increments from branches of TOT. So here we have X, Y, and Z depending on how deep you are. So one thing to note here is that this means we can't branch from a branch of a branch. There's no fourth digit, so the version number wouldn't make sense at that point. It would be invalid. And this breaks some infrastructure, so we try not to do that. uh, this versioning structure is really handy, though. It makes it easier to reason about what the contents might be for a particular version number. So you can infer from some other, and you can infer other properties of this. Like if the second digit or minor version is a higher value, it means we've built that on top of a branch for longer. And so it might just be more stable than a build with a smaller minor version value, as an example. But it's really handy if you're looking for where did something land and what do I have in my build. So now let's talk about merging CLs in Chrome OS. We need a way of making release branches stable after all, and they're not likely to be perfect when we first cut them from TOT as much as we try to make sure we test on TOT a lot. So Chrome OS is a TOT first project in that all development is done against TOT. This is the inverse of some other projects where work may be done on a particular release branch and backported to TOT, but Chrome OS strives to keep TOT releasable at all times, even if it is in a lower stability and quality state, as you might see on Canary or Dev. Uh, all merges to release branches are bug fixes only. We don't want to develop features on release branches such that we can preserve their stability. Chrome OS is effectively stabilized by this merge policy and process. All merges to release branches are done under strict criteria and review. So what might a typical CL's flow look like in this regard? By default, a CL might actually take quite some time to get to a stable channel user. The bulk of our user base is mostly stable. A CL can land just after branch point, and it would not be on a release branch for nearly 6 weeks. Then it would be even longer before that's actually able to promote to stable, and the majority of users would see it. Now, this is largely intentional. The longer a CL takes to on TOT, and that it takes to flow through the release branches, the more likely we are to catch any regressions that it might cause. Uh, So catching these regressions in an ecosystem level product like Chrome OS is hard to do with just testing. So having the CL available on Canary, Dev, and Beta before going to stable helps us to ensure higher quality. However, in some cases, we do need to move faster, such as if we find a bug right before a stable release, or even after a stable release is out in the field. And in this case, if a bug is particularly critical, the CL associated with it may be approved to merge into a release branch, which brings the availability timeline of that CL in substantially. This is great for fixing things quickly. However, we have to be cautious in doing this, as the same CL that is fixing one bug might unknowingly cause another bug. As such, CLs that get merged directly into stable are going to be vetted before merging, generally requiring that they will be very well tested, possibly even live on a lower channel like Dev or Beta for some amount of time before bringing them into stable. This is ultimately a judgment call by the owner of the release milestone. So we can make builds of Chrome OS and we can isolate our changes down to stabilize these builds. How does the user actually get the build? Here we'll talk about some automated update mechanisms. Now, note that most of these tools aren't really available to the public. You can see source for some of it and you can see them references, but the concepts are still useful outside of the team. And you can actually see a lot of what's happening with the update mechanisms on a device. So, the auto update process is broken into three main pieces. We have our release console called Goldeneye. This is an auto update service called Omaha, and a bulk binary distribution service. We'll call that dl.google.com. Uh, GoldenEye drives the release process mechanics. It effectively handles the flow of testing and configuration of the auto update mechanisms. When a new release goes out, it's because a release owning TPM has pressed the push button in GoldenEye. Omaha is what actually tells the device what update payload to get, and dl.google.com hosts the actual payloads. It's capable of handling the substantial bandwidth needed for a Chrome OS update. So, how does the flow actually go here? First, there's an update engine service on every Chrome OS device. This runs in the background and periodically checks for updates. When checking for updates, it sends an update request to Omaha. You can actually see this if you go into file://var log update engine on a Chrome OS device. Uh, and an excerpt of it can be seen here. All this has is basic metadata about the device, like what kind of device it is, what version it's running, and what channel it wants, so that the Omaha update service can tell it what version it should download and where it should download that. So what happens next is the Omaha service processes that metadata sent by Update Engine and runs it against a set of rules which are generated by the GoldenEye tool. These rules define what payload should be served where and in what conditions. For example, it will have rules for dev, beta, and stable channels for each device that specify what versions they should receive. Omaha will respond to Update Engine with the metadata needed to actually retrieve and install the update. You can see this in the Update Engine logs on a device just as well. And this has more basic stuff in it, what you might expect, the URL, where to get it at, uh, a signature to verify the integrity of the payload, what version it is, how big it is, like all this stuff is in there. And it's all fairly straightforward. So the Update Engine service will take this and download the payload from dl.google.com and install that payload. This involves expanding the payload into the partition that is not currently being run from. We do use an A/B partitioning scheme, and performing other actions like updating firmware as necessary. So when the update engine is done installing, it passes a flag up to the stack to let the UI know that an update is available. And that is when you might see the update available notification on your device. From there, it's up to the user to reboot the device to put the new OS into effect. So, taking a step back, the overall flow looks something like this. GoldenEye configures updates on the server side, Update Engine makes requests and installs those on the device side. And with that, we've actually completed the full flow from a CL all the way to an end user. So thank you all for taking the time to attend this presentation. And we now have a few minutes for questions. Oh, I see Hardik asks, why would you branch from a branch to get the last number on the cross version? We normally use these for the purposes of stabilization. So as an example, let's say we have a device that needs a change very badly. However, this change uh, is maybe risky and we don't want to necessarily ship it to all the users at once. We can take a release branch and branch from that release branch, put on this somewhat risky change that's really needed for one device, and then ship that particular version only to that device. So it allows us to isolate changes, really. That's a good question, though. But I think that's the only question I see. So, any other questions? Okay, we can give another few seconds here. I see if anybody else asks anything, but otherwise, I think we're probably good. All right. Well, if no other questions have come in, I think we can call that the end. So, thank you again for taking the time to attend this talk, and have a nice day.